So let's get started. So yeah, thank you very much for that introduction, Jay. I'm a PhD student, so I will say I'm not a world-leading expert by any means on this method, but I have been working using some of these the quasi-experimental methods, including interrupted time series analysis. So hopefully, my aim here is to just try and give you somewhere to start if you're either thinking about doing this sort of analysis, or just give you a bit more information about how it works. So in the future, it might help you think about some new ideas that might be useful in the future. So so during the presentation, I'm just going to start with giving you a really quick overview of quasi-experimental study designs, and then focus on how an interrupted time series analysis actually works. Then if we've got time, I'll work through a very basic worked example. I'm afraid it's not going to be super detailed, but hopefully, again, it will give you somewhere to start if you ever want to be doing this sort of analysis yourself. There'll also be some time for some questions and discussions after that, as well as I think I've planned in a couple of little spaces, as Jay mentioned, but for questions. So if you do have questions, put them in the chat, or if you make a note, and then there'll definitely be opportunities to ask them. And then I've also got some useful literature and bits and pieces that might be handy for you in the future. So if we Sorry, my computer was being a little bit slow there. So if we start with quasi-experimental study designs, so these kind of occupy the space in between a randomized control study and observational studies. And they tend to be used when to assess an intervention or an event, or the effects of an event, when randomization is either impractical or unethical. So the very basic example would be it's a pre-test, post-test analysis. So you're looking at the conditions before and after an event. So for example, if a useful example might be thinking about looking at children's reading age in a classroom, and then you have an intervention where maybe you start library visits, and you might see how that affects their reading scores before and afterwards. There's obviously issues, though, as I'm sure you're all thinking about with that. So you might add in a non-equivalent control group. So you might have one classroom in a school where they get the library visits, the intervention, and one where they don't, and then you compare any differences beforehand. But again, I'm sure you all are working in research, can definitely be thinking of huge red flags about what some potential issues with that. So to combat this, there are some more complex quasi-experimental study designs that can maybe take into account some of those confounders or other sort of trends. So, for example, the one that we're going to be focusing on today, which is interrupted time series analysis, we're able to look at the change in the trends both before and after your intervention, as well as that specific change in reading scores. So, which is really important, especially because if we go back to that example of looking at children's reading scores, you're expecting them to be to be improving throughout your school year. And so you don't know if so this way you're hoping to be looking at, does it give them a boost that keeps on going up, or does it give children a boost and then it kind of goes back to normal, or that sort of idea. You might also add in a control group, and then there's also other similar but different interrupted quasi-experimental study design. So specifically, I'm thinking of regression, discontinuity, and a difference in different study designs, which I'm just going to go into in a little bit more detail here. So the reason I'm focusing on these three factors is because while a statistician or economics person may mildly shoot me for saying this, the nuts and bolts of how you do the analysis is comparable, and they are probably they do slightly blend together. And again, you see this when you're thinking about different observational study designs, like identifying exactly which one's which. Some things have a little bit of, some things are very clearly one thing and not like cross-sectional study and not a cohort study. But the difference between a cohort study, you might have a cohort that's got a case control nested in it, or, you know, these things. So anyway, just very briefly, an interrupted time series analysis is looking at to analyze the trends in a single group over multiple time periods. That is unless you're obviously adding in a control group. It's very good at analysing the impact of a time-delimited intervention, something that may be continuing or introduced and then continues, or is introduced and then you want to see how that affects the post-intervention period. Regression discontinuity design, it doesn't necessarily have to be a time delimited segment of the population, although it still can have that time series aspect to that sort of analysis. But the key thing with the regression discontinuity design is you're assuming a randomization around a specific cutoff point. That could be in time, but it could also be within space, so different areas, for example. And within a regression discontinuity analysis, you're looking at the local effects around that cutoff period, that cutoff point within a single group. And it also doesn't require something called a parallel trend assumption, which I'll talk about in a little bit more detail in a couple of slides' time. And the parallel trends assumption is also crucial for something called a difference in difference analysis, where you're looking at the trends in a treatment and a control group, and assuming that your treatment group would have had exactly the same trajectory as your control group, you look at the difference between those trajectories pre and post intervention. So sometimes you can add in a sort of a difference in difference approach within a regression discontinuity or interrupted time series analysis, or you can kind of do it on its own. But that's what I mean by it's kind of that they do overlap. But yeah, so I hope that's clear enough for now. Although if again, we can clarify anything if need be. But as I said, I'm very sorry, it's a bit of a whistle-stop tour. So moving on to some of the concept of how an interrupted time series analysis works. So the most essential thing that you need is to conduct an interrupted time series analysis is a data set with a repeated consistent observations of your outcome over time. So what I've just got a graph here with referrals, doesn't matter what for, and then weeks, and a weekly count of the number of referrals that are made to a fictional service over 30 weeks. So that's something that is quite easy to consistently observe because it's quite an easy thing to classify. But one of the key things is that before and after your intervention, you're not changing how you're measuring your outcome. So the next thing that you're going to need is your intervention, which needs to have a clearly defined intervention date. And we're assuming that as well to be the only factor in the population of interest that is changing, that you're observing within, that is going to change your outcome. So that is always something to be mindful of, especially when you're thinking about things conceptually or discussing your results, so to speak. So when I was looking at the COVID lockdown, for example, that was comparatively isolated compared to a lot of things that you might be looking at with an interrupted time series analysis. But we also, it's also important to be considering it's not just that policy change, there's also economic downturn that was happening around that time, or time of year, that sort of thing. So we're then going to be measuring our outcome, as I said, after that intervention in a consistent manner, and seeing how that changes. So what we've got is we would be first looking at the sort of this initial trajectory, and this is the parallel trends assumption. So before the intervention, we're seeing this kind of positive trend upwards, and we would be assuming that would continue in exactly the same way after your intervention date. And to keep things simple, trying to model this linearly. Again, you can do more fancy things statistically to look at something that's maybe a more complex trend. But if it's flat, you assume it's flat. If it's negative, you're assuming it's going to remain negative. We would and that's what we're going to be looking at in the analysis. So we're going to be assessing two specific factors. So the first of those is the change in the level of the outcome that's associated with the intervention. So for here, we've got our kind of referrals, which are sort of hovering at around, what is it, maybe 135. And then there's this big jump up, again, obviously in this fictional level data set, to 175 referrals per week. So that's your level change that's associated with that intervention. Then we're also looking at this slope change. So the rate of the outcome following the intervention is the second thing that we're going to be really trying to assess. So it's not just what changes, but it's like how long will that change potentially last? Or what is the continued thing? But the key thing as well is that we are segmenting our regression between around this intervention date within a time series to look at the level and the slope change that are associated with it. If we want to add some rigor within our interrupted time series analysis, there's also potential to add in a control period or work within more data from multiple sites with multiple different characteristics. So for here, if you look at this sort of yellow graph, part of the graph here, if that was our control period, we're looking at this, we're assuming that this sort of trend it's obviously different to what we're looking at in our intervention group. That's a different angle here. But this trend we're still seeing is pretty consistent throughout in our control period, in our control group, which would then add some validity as well. Or we would be looking at this kind of like, which would add some validity, sorry, to that parallel trends assumption, which we would be employing to a certain extent when we're within our assumptions, when we're estimating this sort of level and slope change. So if there was a sort of a similar up and then similar sort of pattern that you saw within your control group that might be happening independently of your intervention, you can look at, you can still see if there was maybe some of that was due to the intervention, or you might even see a completely opposite pattern within this. But anyway, that's a control group, which is a kind of an additional extra that you can add to your interrupted time series analysis to improve its rigor. So there are some key factors that you want to be looking out for when you're running an interrupted time series analysis, both within the data and at the sort of more theoretical conceptual level. So again, I'm going to whiz through this, and I'm not going to go into a lot of detail about what all of these factors are and how to measure them. I'm sorry about that, but just as a kind of, just do some really quick flags about these are things that you're going to need to check for, be aware of, and a little bit of a note about how to at least address some of them. So the first problem that you're going to be looking for is some within your data is autocorrelation. So this just refers to that period. So it refers to a breach of the assumption that each data point within the time series are independent. So we would be assuming, if we're looking at referrals, we'd be assuming that the referrals in week 2, if they were quite high, you would assume that the rate of referral on week 3 is completely, whether that's high or low or about normal, you assume that that has nothing to do with the referrals in week 2. However, you might actually see in real life, so for example, there's like lots of examples that you might see. If you've actually had a lot of referrals in week 2, you might see a kind of dip in week 3 just because there's only a finite number of people that might be needed to be referred to your service. Or conversely, you might see another high sort of referral day, be more likely to see another high referral day on week 3 after a high referral week on week 2 because of some other factor that I'm sure you can imagine. So we can address this and correct for it statistically using appropriate regression models. You can add in you can account for that within your analysis as well. Again, I'm not going to go into a huge amount of detail about it, but hopefully as well, when you're addressing some of the other factors, especially what I'm going to talk about next, which is non-stationary data, if you address that, that can sometimes account for some of the what might read as autocorrelation when you're looking at the diagnostics of your regression model. So non-stationary data is basically is when you have a repeating pattern within your data set. So the key example of that is normally something like seasonality, but there are plenty of other things that you might see, and you might already have an idea of what they are, like seasonality, but there may be things that turn up, or you might identify in your data set. When you're really just like when you're visually analyzing it, you might see some patterns. So ways that you can address this and account for those effects within your analysis is using a control series within your interrupted time series analysis. There's also a type of robust statistical modeling called autoregressive integrated moving averages modeling, or ARIMA modeling. These models it's a family of regression models which are specifically sort of designed and constructed to address things like autocorrelation and non-stationarity in your data. However, I haven't personally ever ended up using an ARIMA model because they also have a lot of other assumptions that you need to make sure your data fits to make it work. But so again, I'm not going to go into details about ARIMA modeling today, and I don't know a huge amount about it, but it's definitely, if this is an issue that you're really concerned within your data, it's something that I would recommend looking up. So then moving on, there's a lagged intervention effect, which is just basically it just is the fact that if you have an intervention and you're modeling it in your time series as a specific change on a specific date, people anticipate that in their behavior. So you might see that in your observation. So in the little image that I've been using, this is a complete absolute level change here. But what you're more likely to see is a kind of a curve going up and then maybe a curve going down, rather than these really straight, nice, clear lines in reality. So you can address for that either by like modeling that lagged period. You might remove like a week from a daily time series or a month from a weekly time series, just to remove some of that just clouding fuzziness around your intervention cut point. Also within an ARIMA model, you can use something called a ramped function to address that. There's also, you have to think about time varying confounders. So it's all, you can adjust for some confounders as you would in any other regression analysis, but there are some things that might change through your time series, and you might want to address those again in varying different ways. There's also conceptually, you need to be taking into account the fact that these are still basically observational studies and are subject to like the ecological fallacy. There's also the big assumption, which is at the core of an interrupted time series analysis or other quasi-experimental study designs, that the intervention that you're assessing is the reason for any observed change. And as we all know, correlation doesn't always equal causation, and you need to really carefully think and discuss the context of like the situation that you're measuring, and the analysis of, and the potential reasons for any outcomes that you might be measuring, or changes in those outcomes. So I'm just going to pause here. If anybody would like to ask any questions, because I want to make sure that it's kind of people have a fairly decent understanding of how like what an interrupted time series analysis is and the basics of how they work before I move on to trying to look at a worked example. But yeah, so I don't know if I hand over to Jay now and then see if there's any.
Do use a chat function, but it might be, Rosie, while we're sort of waiting for people to think of questions, it might be that people have questions after they see your example, because it's helpful sometimes, isn't it, to see a real world
For sure, yeah.
example. But just very quickly, something that occurred to me, and I think you're probably going to go on and speak about this. You talked about a sort of lagged intervention effect, and I can't recall if this is in your example, but you're going to specifically talk about the COVID-19 lockdowns, aren't you? So, in a situation where people are starting to change their behaviour before a policy takes effect, and we know that, for example, social distancing measures were introduced prior to, complete lockdown. How do you decide that time frame where, you start to see a change in the trends? Do you use policy, or are you just looking at the data and using that to decide how you might introduce a kind of lagged effect? Can you say something about that?
Yeah, so I think it's kind of, again, similarly with any other observational analysis, you're thinking about both the data and what you're seeing, as well as what you know is happening in the context. So with the COVID-19 pandemic, we knew that people were already changing their. So if you're thinking of, so we were modeling the cut point as 23rd of March, but already in sort of mid-March, people were changing their behavior. That was when, again, if you cast your minds back, that was when people were panic buying toilet roll, and you couldn't get anything in Sainsbury's, you couldn't get any chopped tomatoes because everyone was buying them and stocking them up in case we had to have a lockdown. So it was something that we were wanting to check for. We also looked at that in the data. So I'll talk about it a little bit more in the worked example, and also try to assess some of that as well, and see if it had an effect within the sensitivity analysis as well, by essentially just removing a few weeks before and after the intervention from our analysis, and seeing if that made a big difference. And in that case, it also depends a little bit on the size of your time series and how many points of data you have. So actually, that is something I feel like I've probably missed, which, if I just quickly say, there are 2 points that I think I forgot to raise. So the first thing is that although rules of thumb are can be a bit misleading, but with an interrupted time series analysis, you obviously need a certain number of observations before and after your intervention. And the kind of rule of thumb is you can get away with about 8 or 9 before and after. But if you've got a lag period and you've only got 8 or 9 observations before and after your intervention, that's going to make a bigger difference than if you've got 100 points before and after your intervention. So
Yeah. Great. Okay, that's really helpful. I can't see any questions in the chat, so why not move on to the example, and there might be questions that arise as you're working through that.
Yes, so I hope so. I apologize again, this is going to be quite quick, but hopefully it will be clear enough. I think time series analysis is something that sounds scarier than it is. So hopefully I'm going to be breaking it down to the essential, just the essentials that you can work with. So and again, I'm going to be talking about data analysis that I've performed using STATA. So I'm very sorry if you're an R user. But again, hopefully it will be again more about how you're parameterizing your model and preparing your data, and hopefully that will be useful for you as well. So the first step is preparing your data for analysis, which is always the most important thing. So the first thing you're thinking about is your unit for analysis. So for me, it's the day. So in the analysis that I'm using as an example is just the day rate. We have a daily count of inpatients that are admitted throughout the whole of SLAM services. So you've got to have an indicator of your unit for analysis. And then your outcome. So as I said, it's that here we've just got the count of inpatients. So just as a note, these numbers aren't the actual counts at all and don't relate. And I've just generated these in Excel to make a table because of confidentiality. Also, the analysis that I'm going to be presenting is going to be slightly different to anything that I will be publishing, just because of it got a bit more complex. But that doesn't matter. But again, hopefully this will become clear. Anyway, so back to this. So you've got the unit for analysis, your outcome measure. And then you've got to have an indicator of your intervention, which is what I said, you're kind of segmenting a regression. So you've got a UK lockdown indicator here, variable here, which is a 0 for your pre-lockdown period or your pre-intervention, and a 1 for your post. You might have multiple cut points, which you can model. Things get confusing if you're not careful, but we'll stay with this for now. And then also you might want to add in a counter that is kind of giving you a separate unit count for your post-intervention period. So I've called this lockdown count in my modeling. And as you can see, the day is going like 68, 69, 70, 71, but we start at 1, 2, 3 on day 70 here, which is when our intervention starts. So it's just an indicator of the distance. That's essentially all you need within your data set. So after you've set it all up nicely, the next thing to do is to visualize your data. This is actually a really important step and you really shouldn't lose it. So as I was talking about with Jay about the lagged intervention period, it will make it really obvious if you have a lagged intervention period. So you can actually see this. This is the data from the COVID time series. So we're looking at the number of inpatients that are held within SLAM. And as you can see, it really plummets down. So but you can see that it's already curving down in early March. So we're looking at to see if that cut point seems reasonable. I've zoomed into this sort of little period here for this graph, but it does seem like it's a pretty sensible point to be cutting the data at. And again, this is something that it's good to check, and it may be less obvious. It's often not as obvious as this, but it's good to check at least that it does seem reasonable, and that when you run your regression, if you were suddenly like looking at this and your results suddenly started pointing to there being no effects, then you would know that there was some sort of an issue going on. So you're also identifying any signs of potential issues within your data, especially thinking about things like seasonality. So you've got this lagged period, which we need to be aware of. And however, again, so in the actual analysis that I'm going to be looking at, this is a small segment, and we have data from the 1st of January through to the 1st of June that I'm including in this, that I'll be presenting today in this analysis. So actually this is less important, less impactful than it might be. But if this was your whole data set, you might really actually have to start doing a little bit more thinking around that lagged period, and if and how you wanted to do something to model that, or add in an extra sort of, maybe add in a sort of transition period from mid-March to the 1st of April, just to model that lagged period as a separate segment of your time series. So have 3 sort of like a anticipatory period modeled as well if you had enough data points. Also, you can see these little spikes coming up. And if you start counting dots, that looks kind of like weekly variation. So it's something that I'll need to be mindful when I'm running my analysis, which is the next thing. Sorry, give me 1 moment. I just need to. Right, thank you. So again, the key thing is start simple. If you're using STATA, declare it as a time series, so TS set date, and then select the appropriate regression model for your data, because I'm using count data, I'll be using a negative binomial regression. and run the model. So it's quite simple. We just have a function here for your outcome, the cut point, which is just a binary independent thing, and then a continuous variable that is describing the post-intervention slope. And then you get a nice little readout of your regression output. Before I go into interpreting what this is, I'm also just going to quickly give an honourable mention to the ITSA command in STATA, which you can add. I have used it and I've never published the results using that. It's less transparent. You can fiddle around with it a bit less if you're prep, but what it will do is it will prep your data appropriately for a time series analysis, which makes things a little bit easier, and it gives you some simplified diagnostics. It's based on like generalized linear modeling. But again, you need to have your data properly structured to use it. But then it will calculate like your lockdown count equivalent and stuff itself. But you can choose to look into that if you want. I've got a link at the end of the presentation. But yeah, so what we're looking for is this coefficient here, which I've exponentiated into an incident rate ratio. We're looking at the level change here, which is the coefficient associated with the UK lockdown variable. And then the lockdown count variable, which will indicate your post-intervention slope change. So you can see the lockdown 1 coefficient, that's 0.704, which is statistically significant. It's quite a definite drop, although maybe not as big as we may have been expecting with the when you were just utilizing data, but it still kind of makes sense. And then also the post-intervention slope change, it's statistically significant, but meaningfully teeny tiny, for want of a better word. So the use of that will depend on the situation and whether or not you're actually going to end up involving this sort of analysis in the sort of the slope analysis within your interrupted time series analysis when you're reporting it. So actually, when we worked through this whole data set, we ended up not including that. It added a lot more complexity to the analysis, which started to hide other results. It wasn't giving us any meaningful information that we thought was useful. So yeah, but I've kind of included it here just to show you. So if we then, I'm just going to skip a couple of steps. So I'll say a note. So if we ran the diagnostics on that initial model, this sort of basic model, it doesn't look good. The residuals are not normally distributed. It doesn't predict the model doesn't predict the actual data very well. It's not well fitted. There's autocorrelation everywhere. So we might start to add in terms for seasonality. So then you get a more complex readout here. But as you can see in here, I've taken essentially the same model, which I've specified. And then I've added in an adjustment for the month of the year, the month of the week, so which day it is in the week, and whether or not you've got a bank holiday Monday, just to address that, essentially those seasonal trends. So you might see more people admitted in January or February than you might in July, because it's dark and people are less often not as happy when it's dark, for example. Then we're looking at essentially the same thing. So these coefficients up here are still going to be telling us the outcomes, the level change and the slope change, which we were looking at beforehand. So this adjusting for seasonality, it has changed the estimates, but it hasn't changed any directionality or statistical significance for what that's worth. But it's still, as I said, it's still kind of important to note that. But then if we run the diagnostics, which I'm going to talk about a little bit more, it's still not looking the best. So the first thing we're going to look for is, deviant residuals and normality of the residuals, as you would with most other regression analyses. How well does the model predict the data? But the key thing that's specific to a time series is looking for autocorrelation. So you can use an autocorrelogram, or something, this command correlogram, which looks at autocorrelation as well, will tell you about will help you identify autocorrelation that is happening within your data that you can't necessarily see or identify theoretically. What this is not what you want your autocorrelation analysis to look like. So I tend to ignore all of these numbers. I'm quite frankly not 100% sure what all of them mean, but what you're seeing, but what the problem is here is these spikes showing a positive, showing so-called positive autocorrelation, that is very, very, very high. So it's suggesting that we are not addressing that within the analysis, because we're looking at the residuals, within the analysis, we are not addressing the fact that each individual point is not fully independent of each other. And when I'm saying here that I'm checking it at 20 lags, so 20 points away, observations 20 days away are affected by ones up here. So for example, the 1st of March would still also be correlated to the 20th of March. But yes, this can all get very technical and complicated. I find that this is the most important thing is just to look at this. If you're getting one, however, just as a sort of honorable mention though, this is the partial autocorrelation assessment. If your autocorrelation did just have one little point here, that was saying that you had a lag of 1, and no other autocorrelation, then you can that's fairly easy to specify in your model. Something like this, you need to do more. So I think I want to leave plenty of time for questions, but just if I just really quickly whiz through the idea of adding a control group. So what we did within the COVID analysis is we looked at the trends of inpatient load or inpatient admissions, not just in the period through 2020. We looked at the same equivalent period, months, sort of the date, but in 2018 and 2016 as well. So the way that you would set that data up is it's almost exactly the same as it was beforehand, but you also add in a parallel group with an indicator as to whether they're in a control group or not. So the intervention still starts on day 20, and then in our control group, which for this I've labeled as with a 2 before the day number, but it might be 2016 day 70 is also when we would be putting the intervention. So while something didn't happen, that's still, we mentioned that happened on the 23rd of March. I hope that makes sense. And then we've got our intervention counter as well. But then we've got this extra indicator. So that is how you can tell the difference between this row and this row within the time series analysis. Then we would then run that as a regression. So I'm sorry, this looks, so as with anything, you model it with an interaction term. So we've got the regression, outcome, and our dependent variable. And then we're looking at our lockdown indicator, our intervention indicator, and its interaction with that binary control group indicator. So we're looking at everything that the change associated with whether it's in, before, or after the intervention. And then you're looking to see, this is where you looking with a difference in differences approach as to whether that change is different, statistically significantly different to it happening to that just period when there was no intervention, but if we modeled it as if there was an intervention in your control period. Which, and then likewise with your slope. I hope that makes some sort of sense. But basically within this absolute mess of an output, you're not going to be looking again at a huge amount, but what we're looking at here is to check this interaction term here for our level change, which is our lockdown intervention, and it's and also the year was 2020. So we're not looking at whether or not there was a significant change in the lockdown associated with that lockdown intervention in 2018 or 19 or 2016. So you can see this. So very basically, you can see that there's actually no change in the difference, which is handy to see. There's no real change. But then when we're looking at our intervention year, that's not the control year, we can see that there is a statistically significant drop in the incidence rate ratio that's associated with the introduction of lockdown. And then similarly as well, we can see that with the slope change. Although again, this is, well, it's statistically significant, technically the slope is still extremely flat. When we're looking at the autocorrelation in the diagnostics for this, as you can see in comparison to the other one, this is much more there's much less autocorrelation to be dealing with. And again, when we parameterized our model properly in the actual analysis, we were able to address all of the autocorrelation. But yeah, so I don't know if you can tell just from looking at this that this looks more healthy is basically what I'm just trying to say. So yes, I think that should be it.